Okay, well, I am, you can hear me okay? Still okay? Really pleased to be here. I think this is going to be a really exciting new series of events, joint events. And this is a topic I've always wanted to talk about, and I've never had the opportunity because we've never had this kind of an event. So as Charles and Katia were putting the idea together, Katia sent out an email, and that's what really got me inspired. She said, and I quote and read, "Hidden corporate stories." Oh man, I got hidden corporate stories. Especially important for young professionals. And this is her quote: "Decide what is relevant to their projects tomorrow and not repeat our mistakes." So I have put together about 5 case studies from my own career. They go back several decades. I was involved in each of these. I've never talked about them publicly, and I don't think anybody else has. I've left out some of the detail, like the companies involved, and that is to protect the innocent, including me. And 4 of the 5 operating companies no longer exist. In each case, I'll end the discussion with a slide where I give you what I consider to be my lessons learned. So we're going to do 5 different case studies. 3 of them are onshore U.S. These are the list of them. And then I had opportunity to work in the North Sea for a while, and I had the opportunity to work in the Nigerian Delta for a while. And those were some very informative foundational lessons I learned there. So let's start in the Eagle Ford Shale in South Texas. And this is a study of, or a case study of an integrated situation where we ended up with a field with 80 producing Eagle Ford wells, and it was totally serendipity. We did not have that in mind at all when we started. We did an integrated follow-up after an initial well, which was drilled for deeper objectives, and we had to incorporate geochemistry, more petrophysics, trend activity. Studying trend activity is a big deal. And ultimately, as I mentioned here, we had 80 successful producers. You'll see how that story unfolds. We had to overcome a conventional wisdom in the industry that the Eagle Ford oil window wouldn't work, that it wouldn't be commercial. That was a pervasive theory, although the gas condensate window was working and it was pretty close to where we were. We got a lease. We were involved in a lease on an 11,000 acre ranch. The owner of the ranch was very depressed. He considered himself, as I say here, snake bit. He was too far south for the Austin Chalk horizontal play, and he was too far north for the gas condensate Eagle Ford play. And so he was excited. We wanted to do something on his lease, but he wouldn't subdivide the lease. So we had to lease the whole 11,000 acres, which made the whole project very expensive. Now, what we did first was we were drilling a Sligo, Cretaceous Sligo Wildcat. This is part of his acreage in yellow. He actually had a much bigger acreage block. And we drilled a straight hole at the where the black bullseye is. Now, our friend, this is a prospect generated by a fellow APG member from Corpus Christi, and he had seen a well drilled earlier on this ranch. The well had shows in the Sligo, but the ranch had never had commercial production. It had shows in numerous wildcats. It had failed Austin Chalk wells. It had wells that weren't deep enough. Well, horizontal drilling was really getting exciting at the time, so we were actually consulting for him. We said, okay, you got to turn this into sort of a horizontal prospect. So he had a key well. It's on the right side, had shows in Sligo. He had a 2D seismic map, which is the little blurb map in the bottom. He thought he was going to drill into an upthrown fault trap on a down to the northwest fault and make a Sligo well. We said, sell it as a horizontal well. Say we're going to drill vertically down, and then we're going to kick at high angle into the Sligo. Great story. You're going to expose more wellbore to the formations and the fractures in the Sligo. That helped us sell the deal. So it was a fairly expensive well. It was about a 12.5 well. And one thing we did when we brought our petrophysicist in, he said, you know, I'm afraid there's a water contact in the Sligo. So you need to keep your horizontal wellbore above that. So we spudded the well, we drilled, and we didn't have a very good well sitter, and we let the well bore lateral drift below the water contact. And although the well was drilled successfully and we had shows, the lateral drifted south. We tested the well, we had good shows, and we had high water cut. The well was non-commercial, we had to P&A it. But when we went through the Eagle Ford, we had great oil shows. So we as consultants said, well, we can't give up on this sucker. So we took the drill cuttings to Weatherford. They did a study on just the drill cuttings. Now this is a plot of depth versus vitrinite reflectance, and we just took a set of drill cuttings to them. They said, yeah, your Sligo, the bottom data point, is in the gas condensate window, but your Eagle Ford cuttings, which are the central data point, are in the oil window. They're mature, they're oil rich. You might have something there. So then we took our logs back to Schlumberger. We had them recompute the logs. And of course, they had experience with the gas condensate play south of us in the Eagle Ford. And they said, you know, you might have something here. So we got excited. Well, we had P&A'd the well. So we said, well, we want to do another well. Let's just re-enter the old well and drill a lateral. We couldn't do that because we had multiple casing strings across the Eagle Ford. Not to be discouraged, we proposed a new horizontal well, and then some of our partners dropped out because they said, you guys are crazy, you just drilled the well and plugged it. We brought new partners in, and we drilled a horizontal well. The map on the right is just a subset of the map I'd shown earlier, 2009. We went back to almost the same surface location. We drilled a vertical well down, kicked it, made a horizontal completion in the Eagle Ford, and it worked. It flowed oil. Now, we did have a clue because there was some on-trend activity where people were drilling to about our depth. We were in a fault block upthrown to the gas condensate play. And because the landowner wouldn't let us subdivide the lease, we had this huge acreage block, but we had to renew it before we could drill this new well. And he wanted to increase his bonus by 50%. We damn near didn't do it, but we did it at the last minute. And the map on the left in 2021 are all the development locations we thought we had. We've drilled almost all of them now, and they're all successful. There's only one well that didn't work, the first one. That's a good lesson, huh? So the lesson here is integration of data, not just seismic and subsurface, but geochemistry, petrophysics, and looking at trend activity. And serendipity sometimes comes in. You can't use it as your main strategy, but it does help. And we are so thankful we had a stubborn landowner, because without his stubbornness, we wouldn't have had the development follow-up potential. But now think about it. This sounds like it was a sort of a logical sequence of events. But how'd you like to go into your management and say, I want to drill a new well because we didn't test the zone in the expensive well we just P&A'd. And, oh, by the way, we got to renew an 11,000 acre lease. But we did succeed in doing that. That caused some indigestion. Okay, now let's go to the Midland Basin. This is another interesting one. It came about as a result of us actually having an opportunity brought to us in which a lawyer recognized that one of his clients had two wells that they owned in West Texas that had big cumes, and no one had ever developed them. So he found a Gulf Coast geologist. He put a prospect together, and that made the deal. The deal came to us. It was a structural prospect for Wolfcamp, and the original drilling in the area had been done by the landowner. This guy is amazing. He went out and actually caused wells to be drilled on his own ranch. As far as we can tell, no geology or geophysics involved. He died. His daughters inherited the ranch. The lawyer put the deal together for them. There was a requirement that never shoot seismic. Can you believe that? Why not? Well, because their patriarch, who had passed away, said, "Oil companies just come and shoot seismic in order to condemn your acreage." A true story. So we put together the prospect. There were two key things that happened simultaneously that were very fortuitous. We had an HGS dinner lecture from an expert in the Permian Basin, and there was a paper published in the AAPG Bulletin about a surface study, an outcrop study, academic study from a German limestone quarry in the lower Triassic. Now, the lower Triassic is very close in geologic age to the upper Wolfcamp, top of the upper Permian, and that was a key piece of information for us. This is what our reservoir looked like. It's limestone, it's fossiliferous. It turns out it's actually a crinoidal bioherm, not a reef, but a bioherm. And it's bryozoans, fusellinids, forams, and corals. Not what you're used to in the, for those of us who worked the Gulf Coast most of our lives. So what happened, basically, the Wolfcamp had these limestone reservoirs. The patriarch had drilled several wells. Two of his wells were fantastic. They had cumed 175,000 barrels of oil from one in the Wolfcamp B and 5 Bs in the Wolfcamp A. And these wells are 5,500 feet. Well, they've never been offset. So I wrote here, a geologist experienced in the Wolfcamp, which was me, had been seen a similar situation on the west side of the Midland Basin up in Ector County. And when I saw this prospect, I said, this has nothing to do with structure. This is a stratigraphic prospect. And then I had the support of the HGS dinner talk and the AAPG academic paper. So there is no structural closure here. This is a shale marker, structural marker in the Wolfcamp. It's monoclinal west dip into the Midland Basin. The acreage involved is the yellow. The two wells that are important are the ones I'm pointing to in the arrow, one gas well, one oil well. He drilled other wells. The other wells basically had mechanical failures or found minor pay in different parts of the Wolfcamp. So here was the study from Germany. What are the chances? And this is similar depositional situation. On the left, you have the down dip organic siltstones and shales. That was the big play going on in the Midland Basin at the time. Horizontal wells in the Sprayberry. But as you come up to the right on the same stratigraphic interval, you develop these biohermal buildups on the shelf edge where the orange and red, and those are porosity zones and permeability zones in the limestone. It's purely a facies change. This was the talk that we had at an HGS dinner from Keith Sklar, who's an independent in Midland. And the play that was so hot in the Midland Basin was on the left side of the cross-section, the deep water, organic rich siltstones and shales. That's where all the horizontal activity is going on still today. But this is greatly exaggerated vertically, but come up on the shelf and you will find a nice carbonate, in fact, limestone, crinoidal, fossil-rich facies filled with oil because it's connected to all the down-dipped source rock. If you go too far to the right, the limestone loses all of its porosity. It's not as fossiliferous and it's dense and doesn't work. When we put the idea together here, this is a series of wells, well bores. It's the only cross-section I've ever made without logs. The green are the zones that had microlog permeability. Micrologs are old-fashioned logs that measure permeability because of mud invasion. So those zones in green had permeability. Then the red are the zones we actually completed. And what you can see from this sequence from basinward on the left to shelfward is the reservoir rock is moving eastward and up dip onto the shelf edge as the transgression occurred in the basin. And then we worked that, since we couldn't have any seismic, the cross-section lower is where we went in and looked for the clean, porous, permeable facies. The yellow is the Wolfcamp B, purple is the Wolfcamp C. They get dense and lose reservoir characteristics both directions, left and right. but there's a fairway of porosity permeability. This is his acreage again. We leased the whole block of acreage. The two sisters who inherited the ranch wanted to keep the old wells. The oil well was still producing. It drilled in 1978. And so we carved out the rectangles of white acreage and we let them keep those wells. Then we infill drilled, and we drilled all the orange dots. That was our plan going in, and they all worked, and they're still producing today. Not great wells, but how about a water-free oil well at 5,000 feet that lasts for 15 or 20 years? Good deal, huh? Okay, lesson learned here, carbonate prospects are a whole different paradigm. The facies and the depositional environment is as important as structure. Carbonate petrophysics is a different animal. It's more complicated. You do need a petrophysicist involved. And sometimes old logs are as good as or better than modern logs. Schlumberger was trying to sell us a huge logging program, and I said, all we need are these old micro logs, you know. Can you do that? And they could still do those. And finally, the literature will sometimes have very important lessons and analogs for you. Okay, now I'm going to jump over to the North Sea. This is a fairly traumatic one. So far I've shown you two successes. This is a trauma experience. We had a license in the North Sea with two exploratory wells from a prior operator. They both had oil pay in the Eocene Balder Formation. There was a puzzling observation I'll get into in just a minute. One well had an anomalous dip meter, the other one had anomalous paleo, and they both had beautiful oil pay, but there was a slight discrepancy in the oil-water contacts. So how did we deal with all that, those anomalous pieces of data? We ignored it. Don't ignore anomalous data. When we developed the field, we actually got an offset license, so we controlled the entire geologic structure. But we developed the field using horizontal wells, long-reach horizontals, and we didn't drill many pilot holes. The UK engineers are so good, they don't need pilot holes. So we just kicked into the reservoir. We had seismic, we had 3D seismic, but it was not very definitive. North Sea has very high interval velocities. The data is much more complicated and difficult to interpret than Gulf of Mexico. We came on production with 13 very expensive long-reach horizontals, and we immediately got a high water cut. We had a brand new FPSO installed, several $100 million investment, and it was basically went to water production. The answer is we were drilling into injectites. Now, have you ever heard of injectites? Raise your hand if you ever heard of injectites. Okay, now you've heard of it. Well, we hadn't heard of it at the time. Here's what's happened. Injectites, well, I'll go back quickly, tell you the two wells we drilled. These are the two old existing wells. Fantastic wells, clean gamma ray and SP, sandstone, beautiful coarse grain, high resistivity oil pay, but the three anomalies. The dip meter on the left well, out of place paleo, the paleo on the left well, the out of place dip meter on the right well, and the oil contacts were not quite consistent. We said, well, they probably have a bad dip meter. Somebody didn't collect the samples correctly, and the water contacts are close enough for government work. Critical mistake. Now, injectites are bodies of sandstone which have been injected up fault planes and fractures into younger strata. They're still connected to the migration pattern of oil in the formation, but they can have very small aerial extents. And in this case, they're connected to the Balder Formation, which is one of the world's greatest aquifers. So basically, our geologic model was wrong. There was information in the literature, particularly about Norwegian fields. We could have learned a lot by studying the literature more. We had another, one of our great challenges was we hadn't drilled many pilot holes, and we were using TVD logs to do our correlation. Well, the TVD log, when you suck all that data back to a TVD log from a lateral, you lose a lot of definition from actually what the log actually contained information. And we didn't have drilling while logging in this. We did have some logging we could do with formation scanning logs or imaging logs, but we didn't do a lot of that either. And as I said, the water cut killed us. Now, we learned a lot. All we had to do was wait about 15 more years. The PhD thesis from the University of Manchester documented injectites in the North Sea. This is the North Sea, the fields out in the middle of the North Sea, Norway on the upper right, UK on the lower left. Injectites are pretty common. There's actually an AAPG memoir, Memoir 87, describing injectites. Here's an example on the right. That is an injected sandstone up into shallower, younger strata, and it comes up a fault plane. It's just remobilized sandstone from a deeper reservoir. That's actually from an outcrop in Angola, and they're in California. They've now been documented in outcrop in California. So here's what the model was. We went into this development. This is a block diagram from Memoir 87. We thought we were just drilling a simple anticline with concordant strata. We thought it was normal. We couldn't resolve that through our seismic or our drilling, and so our model was an anticline indicated by the red correlation lines. Here's what it really was. Same block diagram, seafloor on the top, and as you went down, you actually had this network of sandstones injected, and we were drilling horizontal wells like the red line is indicated, and every well had pay. I mean, we had multiple zones of pay. We'd get shows. We just had wonderful outcome, and our mantra, which really was what was misleading, is we tell management we needed we're a little bit worried, we ought to do some more logging, maybe we should do some extended production tests. And the answer was, shoot, man, every lateral's got oil pay, what are you worried about? What could go wrong? Well, what happened was, I'll get the killer slide here in a minute, the 2021 PhD thesis, he had enough data to define sand bodies, and this is what they look like diagrammatically. It's like the salt in the Gulf of Mexico, where you have sills and dikes of salt. These are sills and dikes of sandstone. Yeah. Occasionally they're big enough to be commercial. This is actually a cartoon we had created when we finally figured some of this out and we tried to explain it. And this is the best illustration I've had of it. So the sandstones have come up and it's almost a floral pattern of sandstone bodies, but they're all connected vertically downward to an aquifer. So what happens, this is again from 87, the block diagram on the left, the oil can migrate up into one of these sand bodies. In that case, and this comes from the Beryl field, gas cap on an oil column on water, but not much aerial extent. If you drill a horizontal well through it and you can't define the geometry, you've basically drilled into several vertical or high angle sand bodies that are all gonna suck water in. And although you've got a lot of pay in your log, it's gonna go to water quickly. So this was a bitter disappointment. What did we do wrong? We didn't have multiple working hypotheses. We didn't take that anomalous data and explain it. We just ignored it, or I should say discounted it. And nature has surprises, and there are clues in the literature. Don't forget that. Keep looking for that. We also had, this might not happen again today because logging while drilling would have potentially solved a lot of the problems. Okay, one more offshore. This is Nigeria.
We have 8 minutes.
It's a similar situation. There were some old wells drilled, had pay, but the pays were different zones. We got a hold of a license. This was out in the eastern side of the Niger Delta. This is 2 maps, the 2D seismic map we started on, and older wells shown in green dots. And then the 3D seismic map we created after we shot proprietary. We drilled high angle directional wells, to try to exploit the field. The cross-section in the center is the diagrammatic cross-section. We were drilling directional wells to get the upthrown fault traps. We were drilling from south to north. It turns out the mother lode we discovered in our last well, which is on the lower right map, the bottom hole location. These were the newer wells. We drilled these high angle wells from south to north. We finally bottomed a well upthrown to fault M, and that is where the mother lode was. That's the log in the upper right corner. And we had made a corporate decision to divest of Nigeria, and just as we found the mother lode, we couldn't convince management to not divest. We sold out, and the follow-up company developed that fault block, and it was quite a prolific field. So as a bitter, unlearned lesson, the geology was successful, but the third company was the one that benefited. So you need to integrate. We could have learned more about this. What we really think happened was the migration pathway was up the major fault, depositional fault, and then migrated the oil into the first trap it got, trapping south of the depositional fault. And so that's the preferred flank, and that's true in a number of the fields in Nigeria. And if we'd only studied the literature more, we could have got a handle on that. Okay, now I'm going to finish with my Austin chalk example, and that is the origin of my artifact out here. The company I was with had assembled a large acreage block in the chalk. This is the cycle of chalk activity. When we first thought we got horizontal drilling, we fixed everything, we could make it commercial. So we drilled a long reach horizontal well. It was fantastic. We drilled it with overpressured mud system. When we got finished, we came out, we let the well flow. We had no drilling logging while drilling information, but we had shows the whole way. We let the well flow back. We were testing 12,000 BOE per day, 15 million cubic feet of gas, 75-foot flare. Pretty exciting. We took an executive field trip to see the well and to thank the Luling operating guys we had in our Luling office and tell them about the big bonuses they were going to get. But we stopped at the well on the way to the Luling office, and our chief engineer checked out the wellhead, checked out the flowing pressures. We went to lunch, took the guys out to lunch. Everybody's excited. We're slapping on the back and talking about what a great deal we've got. We have enough acreage to drill 18 more offsets. But on the way back to Houston, the reservoir engineer, chief engineer, said, let's go look at the well again. We had drawn down the flowing tubing pressure 10% during lunch. That's bad. He said, we got a real serious problem. Now, we thought he was crazy, being too conservative, but he insisted, and we got more data. We thought we had reasons we could explain it. Hyperbolic decline, migrating fines, but it was all incorrect. We were depleting the well on test. So what did we do? We made a press release, but we didn't know we had made a press release right after we started testing the well because it was too significant to not make a press release. So the press release showed up on the front page of the Houston Chronicle, which I have in my artifact. And this is the front page of the Houston Chronicle. It's not the business section. The reporter actually took the press release and he created a great cross-section showing horizontal drilling to connect multiple fracture zones in your lateral. Then he put an article in the newspaper that we're gushing over our oil find. Meanwhile, back at the ranch, we know the well is depleting, and we had no idea the reporter was going to make this kind of an announcement. Well, there go the bonuses. And as a matter of fact, we were getting really worried. We're going to get accused of misleading the SEC. So anyway, that's how that turned out. We sold the well for salvage after about 9 months on clearinghouse. And the incredible thing there was the chairman, CEO, told us to farm out the acreage, and we did. We farmed it out for $1 million cash payment and a commitment to drill the 18 development wells. The next company decided it was non-commercial and also left. Final bitter lesson. We avoided the bitter lesson. We passed it on to the next company. You got to integrate your data and deal with everybody, particularly the reservoir engineers. Despite everything Pete Rose has told us, I'm afraid it's still true. Geoscientists tend to be optimists. Reservoir engineers are realists, and you got to work with them and make sure your data is integrated so that you don't pull a mistake like this. So that's my story. I hope that's helpful, and maybe a little bit of humor there. It wasn't funny at the time, I can assure you. And this artifact hung on my wall in every office, and I told that story to every young person that came to work for me. Be humble. Nature's complicated. Thank you.